So next we are going to talk a little bit about samples and populations. When we are doing any research, it is important that any sample that we take is as representative as possible as we can make it, so that the results can be extrapolated to that particular population. And the best way to do it is to do and get the most random sample that we can generate. So if the sample is random, then we can get a representative sample which will reflect the entire population. Yet, our focus is never on the sample, because our focus of interest is the information that the sample can provide about the entire population. So if you are clear about this concept, which is absolutely basic, simple, and nonsensical, this is elementary in the concept for statistics, that you get the information from a sample, but you are more interested how does this relate to the entire population from which this sample comes from. So now let's talk a little bit about distributions. Again, not a very difficult concept, although everyone wants to believe that this is a very difficult concept. And let me again engage my pen in this. So we have binary distribution. Obviously, we know what is a binary distribution when the answer is only yes and no, and there are only two parts. There is going to be a binary distribution. If the question is, are you married or unmarried? There can be only yes and no. So then that's a binary distribution. There is something called a Poisson distribution, which most of you would not come across, but we will talk a little bit more about this on the next slide so that it doesn't appear to be so archaic and so mundane that you don't know what it is. And you are taken by surprise if anybody talks about a Poisson distribution. And obviously the normal distribution, which everyone has grilled into you so far, that there is a normal distribution. So that's a normal distribution. Some graphs here to show normal distributions. You have a peak and you have the tails on both sides. It's symmetrical from the center. It's usually the most common one that you will see. It's entirely defined by two values and properties. One is the mean and standard deviation. That means और कुछ उसके अंदर बताने के लिए बचता ही नहीं है. There is nothing left to explain about a normal distribution if you have told the mean and standard deviation, which are just the two properties of that particular distribution. The mean, as you all know, determines how high the peak will be, and the standard deviation determines how spread out the graph will be. So here in this graph, in this top panel, you see that these three graphs have got different means. This one has got a mean which is higher. This has got a mean which is 0. And this has got a mean which is -2. And they have got different standard deviations also. This is a narrow one. This is a broad one. And this one is even broader, the green one. In the lower panel, you can see that all these have got the same mean. They have the mean at 0. They have the peak appearing at the same time. But if the standard deviation changes, the width of the graph has changed. So that can visually tell you how the mean affects the distribution and how the standard deviation affects the distribution. So I hope this is clear and there is no problem in understanding this. Mean जितना बड़ा होगा, peak उतनी ऊपर होगी, और standard deviation जितना बड़ा होगा, उस ग्राफ का फैलाव या spread उतना ज़्यादा होगा. So this is something that you just need to get intuitively, but nothing to remember or nothing to learn by heart at this point. So talking about a Poisson distribution, it talks about just random haphazard occurrences, जिनका कोई order नहीं है, जिनका कोई तरीका नहीं है. Let's say, how many bulbs will fuse in 1 year? There is no order. ऐसा नहीं है कि एक ही होगा या दो ही होंगे या there may be 3 fuse. If you follow how many bulbs fused every year, one after the other, They're just random, they're haphazard. How many times the lightning will fall in the next minute? You don't know. It doesn't depend upon the previous minute. These are rare events. They're binary events and occur independently or at constant probability. We don't know when this will happen, and they're random, just random. So a characteristic of this kind of a distribution is just that the mean is same as variance. In the previous one, we saw that mean and standard deviation are two different characteristics which describe a sample. In a Poisson distribution, you will find that the mean and variance are both equal to each other. So that's it. We are not going to talk much about Poisson distributions unless any one of you can give me a clinical example from gynecology where you might find a Poisson distribution. But other than that, rarely we will find this in clinical practice. Some more concepts, something called the reference range. Now, a reference range, they have already grilled these into you. There is the mean plus 1.96 standard deviation. So if you minus it, you will get a lower number. If you add 1.96 standard deviations, you will get a larger number. So every value that appears in between mean minus 1.96 SD and mean plus 1.96 SD forms the 95% reference range, which only means that 95% values of your distribution of your data will be between this reference range. That's all. Nothing important, nothing rocket science, nothing complicated. Why is it important to check? Because it can be misleading if the data is skewed. Supposing you thought that the data was normal, but then you find that the level of HB is coming at -2. That means there is a problem. Either your data is skewed or there is a problem in some values which have been entered wrongly. That's why it's good to check the reference ranges. There is something called the standard error. So if you remember in my previous slide, I told you that when we take a sample, we are really not interested in the sample. We are interested how much and how well. Yeah, I think somebody has forgotten to mute their mic. That's okay. We have a standard error. We were talking about standard error. And like I was saying, you're not interested in the sample. You're not interested in what information the sample is giving you, but you are interested in what this information can tell you about the population from which the sample is coming. Now, what we saw was in a sample, we have got something called a standard deviation. But in case of a population, we talk about a standard error. It's just when you're moving from a sample to the population, you realize that the estimate of a population is to be drawn from a single sample. Can you imagine how tough and how problematic it is? We have just taken 15 people or 20 people or 100 people, and we are trying to talk about the entire population of India. It's a little glum and a gloomy situation. But the advantage happens that if many such samples are taken, or if we are able to take all possible samples of the entire population of India, and we have taken millions of samples of 100 people, we might have included everybody. Another good point is that the distribution of the means of many samples. Now, listen to me very carefully. If you have many samples, just pay attention to me for the next 2 minutes and you will never get confused with this problem of standard error. I do understand that this is a very confusing term and a lot of people make a mistake in misunderstanding what is standard error and what is standard deviation. So please listen to me carefully. When we are talking about one sample, you're talking about standard deviation. Now we are talking that if from this population of India, we were able to take many small samples and we took the mean of each sample. And after we took the mean of each sample, we then tried to see how this mean is distributed. And the distribution of means of many samples is always normal. So please remember, when you have many samples from the same population and you are studying the means of all these samples and plotting their means, they will be normally distributed. That is a very central concept in entire Bayesian statistics. And this is how the entire statistics revolves around what is called the central limit theorem, which gives the magic number of 30. That means if you have more than 30 samples, then practically the means will always be normal. Less than 30 samples, it's a little near normal, but beyond 30 samples, everything is normal. The means will always be distributed normally. The variability of these sample means, so when you have plotted the sample means and you have found them, they are normal, then the variability or the variation that is found in them is called the standard error. So standard deviation was from one sample. Standard error is the standard deviation of all the means that you have found from different samples from the entire population. I hope that I have made this concept a little clearer to you. But if you have been listening attentively to every word, then it will become intuitive. You don't need to remember it. It'll just become intuitively imbibed by you that when it's one sample, it's standard deviation. But when you are plotting the distribution of the means of all the samples, what you get is the standard error. The standard deviation will always be more than the standard error. So in many articles, you might find that they want to mislead you and they will give you a very narrow standard error, making you believe that our study was very good. But then it is not the standard error that you are interested in, but you should be reporting the standard deviation depending upon why the study was done. So when to report standard deviation, when to report standard error. So if the purpose of your study is to describe, and it's a descriptive study, I want to describe or I want to see what is the hemoglobin levels of all pregnant patients, then I want to report the standard deviation. But if the purpose of my study is to estimate the hemoglobin in a population of people who are living in India, then I report the standard error. It all depends upon what was the purpose of your study. So much so about standard error and standard deviation. Let's move to another concept, which is called the confidence interval. And I promise you that if you pay attention for the next 5 minutes, you will be clear about the confidence interval also. So if you remember, 95% reference range includes 95% of the values in the sample. We just now said that the sample means are normally distributed. No problem with that. So let's say the range of values in which 95% of the sample means will lie becomes what we know as the confidence interval. Because the population mean is unknown, we really don't know what actually is the mean of the entire population. 95% confidence interval is obtained in the same way. It's the range of values in which the true population mean is likely to lie. We don't know where it is going to be, but we say it's likely to be in this range that we determine from what we have done in one sample. And to determine the 95% confidence interval, we take the sample mean that we have found from our study, from whatever study sample we have. We take the sample mean, subtract 1.96 standard error. You see, when we were doing the reference range, we were doing the same thing for the standard deviation. Here, we are doing the standard error. So when we minus and plus, So we get a range for a low value and a high value, and everything that lies in between becomes what we know is the confidence interval. So remember, sample mean comes from the single sample that we have studied, and standard error is derived again by the software from the same manner. And when we add minus and plus, we get what is confidence interval. That's how it will develop it. And when we say 95% confidence interval, that means we are 95% sure that the true population mean will lie in this confidence interval that we are giving you. Still, 5% chance is there that it might still lie outside, but 95% of the time it will lie within these values. That's what is confidence interval. And there is nothing else or no other rocket science between confidence interval and sample error or standard error. There's one small problem. What we have done is just one sample. हमने तो एक ही sample लिया था. The entire estimation is dependent on one sample. We never know where this sample came from and how representative it is. If you remember this normal distribution, it is possible that this sample is actually taken from this area, or it might have been taken from this area. If it is taken from this particular area, then the mean that is coming from this sample is also from this area and may not represent 95% of the population. But if the sample was drawn from this area, then it's 95% chance that it will still give us the right population mean. But the problem is that we really don't know which part the sample represents. And that's the entire crux of our statistic. Because given a 95% confidence interval based on a single sample, you can be only 95% confident that the true population mean lies somewhere within the range that you have specified. But please do remember that 5% of such intervals that have been computed will not contain the true population mean. This is all that we have about confidence intervals, and we make two assumptions while doing this confidence intervals, that the distribution of means is normal, which we saw if we have more than 30 samples, it is always normal. And the population standard deviation can be approximated by the sample standard deviation. So population standard deviation was the standard error. And so our assumption is that it's okay to estimate the sample standard error just by doing one sample ka standard deviation. But if the sample size is very small, then we solve the problem because it is not normal any longer by what we have is called the t distribution. Again, I don't want you to get confused, but please remember that even if the sample size is small, we have ways of reaching to the same kind of confidence intervals, the same kind of standard errors by using, instead of a normal distribution, a t distribution, which is similar to a normal distribution, but just has got longer tails. So if you see, this is the normal distribution, which is called the Z distribution. And the T distribution is just the same, but it just has a longer tail. In the red graph, it's the sample size was 30, which was our magic number. But when it gets smaller, the T distribution has got broader tails. That's it. But we use, instead of doing our approximations and calculations on a normal distribution, we do it on a T distribution. Once again, this is nothing you need to do. There is nothing you need to know. Everything the software will do it for you in day of 2022, and you don't need to do it by hand any longer.